All right, so today we are going to start the final lecture. We are here in person today. Now, I have uploaded the final lecture to the Google Drive folder. Let me just share that with you. So, when you go to the Google Drive folder, um, if you check the course outline, so we have covered all these lessons, and we are finally at the nonlinear differential equations and the applications, the differential equations first order linear form applications part, and then we will be done with this particular MEcon 503 quantitative economics course. And I have uploaded the lecture 10 that we're going to cover, um, and you can download this note. And also, I have uploaded a few problems and solutions for lecture 10 as well. So you can maybe go through those problems to practice along with the solutions. Few problems without numerical values and few problems with numerical values as well. So you can go through that. And I have done that for a few other lectures as well. And you find problems in the lecture note too. Um, and you can find some problems in the reference material I've given, such as Alpha C. Chang's book. He gives a lot of problems in his book as well. And Shom's Introduction to Mathematical Economics, that book will also have. And I've also given another references material PDF where you can find few other references as well. And in terms of papers, so I've uploaded the mid-semester paper along with the answers. I've uploaded another model paper for the mid-sem. And as promised, I will upload a final exam model paper as well. The past papers also have been uploaded here, 2024 and 2023. And yeah, so maybe go through all of this, and the YouTube online recordings also I've given here in case you missed them. So let's get into today's lecture. So today's lecture is quite important. Um, so we will be looking at first order differential equations in economic dynamics. Now we've been studying prior to this integration, prior to that differentiation, parts of very basic parts of calculus. But in this case, it's a culmination of all of that. So what does first order differential equations mean? Let's try and break it down to make it a little easier. So we first have the terms first order. So first order is very simple. In differentiation, if I have a function y of f of x, if I want to differentiate y with respect to x, I take dy by dx. So this would be a first order differentiation. If I want to take the second derivative, I take d squared y by dx squared. That's my second order. If I want to likewise take the nth order, dny by dxn, that will be the nth order derivative. So here we are only focusing on first order. So we do not have any of this in our equation. So that is what is meant by saying first order. Right. Then it's a differential equation. It's a linear differential equation. The next time we're looking at is linear, which means there are no quadratic forms or cubic forms in it. It's all in linear format. And the specific um, equation that we are looking at is in this form onto your left hand side. So if I write it down, the specific standard form for first order linear differential equations is dy by dt p of ty equals q of t, right? So this is the most basic thing that we will study on the first order linear differential equation. Now, you may wonder, why are we learning these things? Now, for example, um, in the stock market, prices change with respect to time, right? And what if someone asks you, okay, can you give me a model to price changes of certain stocks with respect to time? So if you do that, your model would consist of differential equations of price changes with respect to time. And if one asks you at a given moment of time, what is the price of a certain stock? That is where you need the knowledge of solving these differential equations. Now, it's not limited to stocks. It can be used in different markets. You can use it in oil markets. You can use it in other commodity markets like gold, silver, any other commodity like livestock, in your energy markets, not particularly oil, LNG, likewise, different markets, right? So a good example of this is the Black-Scholes model that is used in, it's a model used to price options market. You have your call and put options. So the Black-Scholes model also consists of differential equations, more complicated differential equations, and also to model things like pathogens like dengue or COVID-19. You use differential equations in mathematical epidemiology. So it's a very highly used, very critical concept that you need to learn because it's a culmination of your knowledge in integration and differentiation. So the most basic form, like I said, that we're looking at is this particular equation, the first order linear differential equation. And when we say we want to solve it, what I mean by that is we want to figure out what y is, right? We want to figure out what y is. That's what I mean by wanting to solve it. Now, in this form, if you will go through the terms, you see, oh, there is a first order derivative. That's nice, dy by dt. And is it linear? Yes, it's linear because you have a function p of t, you have your y function, which is also a function of t, a q function. None of these are quadratic or cubic. It's all linear. So linear means uh, appear to first power and are not multiplied together. That is of this form, right? So that is what linear means. So it's linear in your variable y. That is the variable you're concerned with. And also, the y is not multiplied with any of its multiples, with dy by dt or y squared, nothing like that. So what we're saying is the dependent variable y enters linearly. Now, in this form, the most basic form one can think of is this form over here, right? Which is dy by dt plus ay equals to b, where what this is saying is it is of this standard form that we just wrote, but in this case, we're simplifying it further by saying, look, the function p, which is a function of time, is a constant a. The function q, which is also a function of time, is also a constant b. So still, this particular equation is of the standard form. It's just that the coefficient of ypt is a constant, and the right-hand side value q of t is also a constant. So let's have a look at how we solve first order linear differential equations, right? That's what we're going to look at next. So in the case of solving these first order linear differential equations, we use a method called the integrating factor method. We use the integrating factor method. So what happens in this? It's quite mechanical. You need to follow a few steps to do this. We are trying to solve first order linear differential equations. So step number one is very simple. Ensure the equation is in the standard linear form. What is the standard linear form? It should be of something like this, right? The variables can change, but it should be of this particular format. And you have to identify what PT and QT are. Second step is the crucial step. That's where the integrating factor, I'll just call it IF, just to be, yeah, so that it's a little easier. The integrating factor will denote it by mu of t. Mu of t is defined by, it's an exponential function with the exponent being an integral of this coefficient of y. So it's an integral of the coefficient of y. And that is how, it's this term over here. That is how the integrating factor is defined. So if your p of t is a constant, things become very easy. Then mu of t equals to e to the power integral of a dt, which is simply e to the power at. After you figure out the integrating factor, then you multiply your first equation by this integrating factor. So multiply equation 1 with equation 2. Then you get on your left hand side e to the power of integral pt dt times dy by dt plus e to the power of integral pt dt times p of ty equals e to the power integral pt dt times q of t. So you write it down like this. And the beauty of this integrating factor is on the left hand side, on this particular side, you see this boils down to very nicely the integrating factor times the variable of interest equals to right hand side, you just copy paste it. Now, why is that? That's critical to understand. Let me just why is that? It's very critical that we understand this because if you notice here, um, let's try and differentiate this, right? Just digress a little bit and differentiate this. So if we were to differentiate this, we would get e to the power integral pt dt times dy by dt plus y times the differential of this exponent. So it's simply the exponent, and not only that, also divided by whatever is inside this. So then you take the you write down the exponent as it is, and then you differentiate um, what is in the exponent, which is pt, right? So isn't that what we have over here in this left hand side? That's exactly what it is, right? So that's the beauty of this integrating factor. It really encapsulates or brings together a lot of terms which are separated out into just two simple terms multiplied together. Now what do we do? So first things first, what is our objective? Our objective is to somehow make y the subject, right? So in order to make y the subject, how can we do that? Very simple. We have to get rid of this differential operator. How do we get rid of this differential operator? You take the integration on both sides with respect to dt. So if you take with respect to dt, assuming that these are differentiable functions with antiderivatives existing, you take the differentiation on both sides. What do I get then on the left hand side? Simply the original function times y. Let me just put y of t. And on the right hand side, I have the integral of e to the power integral of pt dt qt dt, right? And then y of t is simply I multiply the whole thing by or divide it, whatever it is, by um, the integrating factor. But for now, without writing the integrating factor in exponential terms, let me write down the integrating factor as simply mu of t. So remember, mu of t is the integrating factor, which is an exponent of exponential function written like this. So then I have y of t is equal to 1 over mu t times the integral of mu t qt dt, right? And that's exactly what I have given on your left hand side over here. Right. So that is the solution that we are looking for. Obviously, uh, in a problem, we have both of them, all the numbers given. So let's take the most simplest form now. Now that's the more general form. Let's take the simplest form where P of t and Q of t are constants. So if P of t and Q of t are constants, let's go through it again. So you have um, dy by dt plus ay equals to b. So then, what is the first step? Check whether it's in the standard form. Yes, it is, where p of t is equal to a and q of t is equals to b, where a and b are constants. It's good to be specific. A and b are constants, right? Then, uh, what is the integrating factor? Step number 2 is the figuring out the integrating factor mu of t. Mu of t is e to the power pt dt. So here pt is a constant a, so that is integral of a dt, which is simply mu of t is e to the power of at. Now I have to multiply the whole thing um, by e to the power of at. So I multiply the whole thing by e to the power of at dy by dt plus, that is equation number 1, plus e to the power of at ay equals to b times e to the power of at. Then this whole thing just simply boils down to d by dt e to the power of at times y equals to b e to the power at. And then I take the integral on both sides with respect to dt, such that I can make y my subject. Take the integral of with respect to dt for both sides. And thus, on my right hand side, assuming that these functions are differentiable and the antiderivative exists, I get e to the power of at times y equals to integral of b e to the power at dt plus, let's take c, the constant value. So on this side, I want to make y the subject, and I multiply the whole thing by e to the power of negative at. I can take b out, and because it's a constant, and if I integrate e to the power at, I get e to the power at divided by a plus the constant. And you see that e to the power at cancels out with e to the power minus at. So therefore, I'm left with y of t equals to b over a, and I missed out over here. This also then needs to be e to the power at plus c times e to the power at. Right. So in order to figure out c, what I can do is I can plug in t equals 0, so that y of 0, assume it's just say y0, some value that's given. Then y0 equals to b over a plus c, because t equals 0, e to the power minus at is e to the power 0 is 1. Therefore, c equals y0, whatever that initial condition value, minus ba. So therefore, your solution is y of t equals b to the power b over a times c is in this case y naught minus b over a times e to the power at. So this would be your solution, is what I have given over here. This would be your solution when you have p of t and q of t as constant values. Now, an important aspect here is the interpretation part of it, this part, and that is key. And key in the sense you also need to understand it. So, what is it saying? So if a is greater than 0, right, I'm interested in this term over here. I'm only interested in this term. What would happen to e to the power minus at if a is greater than 0? You get this term is in the form of e to the power, let's say, minus x, of that form if a is positive. So how do we graph e to the power minus of x? Y equals e to the power minus x is something of this form, right? And then y equals it, if I increase the coefficient minus 100x, let's see whether we get it. There we go. See, it quickly comes down, right? It approaches, it quickly comes down. Now what if, what I'm trying to say here is e to the power of minus at, when a is positive, it decreases over time, right? Oh, it is decreasing over time. Assume this x-axis actually over here, this x-axis is time, and this y-axis over here is our function e to the power minus at, whatever y, right? So you see the function e to the power x is decreasing with time. That's what's happening, right? And in my original solution, as time goes by, this is decreasing over time, and as t goes to infinity, what is happening is that y of t approaches BOA. Why is that? Because when t goes to infinity, this e to the power minus at, the term goes to 0. Therefore, we are left with, as t goes to infinity, when a is positive, y of t goes to BOA, and that we say is corresponds to a stable equilibrium. The system returns to y star over time. But what happens when a is negative? That's key. When a is negative, e to the power minus at grows exponentially. Why is that? Because the term becomes positive. When a is negative, this term becomes positive. For example, you have e to the power minus 2t, e to the power minus, let's say a is negative, say minus 2. That means it is e to the power 2t. So how do we graph positive exponentials? Y equals e to the power x. It looks something like this. It's growing exponentially. And if I increase the coefficient value, it will grow much faster, right? Let me take a smaller value. So taking this one, we did this. Set graph. And let's take y e to the power 30x maybe. To existing graph. See, it quickly rises up, right? And that's what I wanted to show you. What that means is, what that means is, um, your y of t, your original equation, which was BOA plus y naught minus BOA e to the power minus at, when a is positive, when a is positive, you get your e to the power minus at grows exponentially, So when t goes to infinity, y of t is just, it just goes to infinity as well, and therefore it indicate an unstable equilibrium in the model. That's what I wanted to tell. Then let's look at a few economic examples. So this is an interesting example. This under economic interpretations, what we're looking at is this market price adjustment model. So assume in the oil market, let's take the oil market. So in the oil market, oil prices change due to various reasons. I'm talking about prices, oil prices, right? Oil prices can change due to various reasons. It can be because of quantity demanded, quantity supplied, politics can play a role, um, um, terrorist attacks, can take a role, sentiments can take a role, likewise different reasons. But assume we are going to model oil prices only using quantity demanded and quantity supplied. So in that case, we're looking at price changes of oil with respect to t given by this particular coefficient k, and the difference multiplied by the difference between quantity um, demanded, difference between quantity demanded and quantity supplied, right? That's how we're going to model this. Now, can we see a similarity between this equation and our original first order linear differential equation? This one. Do we see similarities between these two? Not at the moment, but maybe we can rearrange a few terms over here such that it looks in the standard format. Okay, let's try and do that. So let's look at this dp by dt equals, that's the original, it's the difference between quantity demanded, which is function of p, and quantity supplied, which is a function of p. So we need to know what qd is. So qd is given by, let's assume, this function, the simple standard linear function for demand, a minus bp. Q, where a and b are constants. QSP, supply, is the standard um, supply curve. Now, usually you would know in your basic undergraduate level first year or A level microeconomics by simply equating QDP to QSP. You can find out what your equilibrium price is, and your equilibrium price you will get as A minus C over D plus B, right? But now we are going to look at it in a more generalized way. So now let's go and substitute in the values of QD and QS. So dP over dt. What is our objective? We're trying to get this standard form. K times QDP is A minus BP minus QSP C plus dP. Let's rearrange some of these terms. I get A minus C minus B plus D times P. So let me take the P values to the left hand side. So I have dP by dt plus K times B plus D times P equals to K times A minus C. Now this equation looks, this equation looks a lot like the original standard linear uh, form that we had, which is this. So in this case, Q of t is this constant value k times A minus C. P of t is this constant value k times B plus D. Your interested variable y is price in this case. So yes, my equation now have successfully converted into the standard linear form. So if that's the case, then I can follow the integrating factor model method. So what is my second step? So first step I have checked. Second step is the integrating factor, which is mu of t equals to e to the power integral pt dt. So what is pt in this case? E to the power, what is pt? Pt is k times b plus d with respect to dt. So that is mu of t is e to the power um, k times b plus d times t. Okay, now I multiply the whole equation by this mu integrating factor such that on the left hand side I will get the integrating factor times the interested variable p, which is a function of t. On my left hand side I will have k times a minus c times the integrating factor. Right. So then I integrate both sides to ensure to make p of t the subject. So I integrate both sides. I write this down with respect to dt, and I integrate this side also with respect to dt, such that on my left hand side I'm left with my original function p plus d times t times y t equals to the integral value of k times a minus c, which is a constant, e to the power k times b plus d times t dt plus the constant. Let me not take c, let me take something like m. So then I can make y the subject by multiplying the whole equation by e to the power minus k times b plus d times t, such that on this side I have minus k times b plus d times t. I can take k times a minus c out because it's a constant, and then I just have to integrate e to the power minus e to the power k times b plus d times t, which is simply e to the power k b plus dt divided by b plus d times k. Hopefully I haven't left anything out, plus m times e to the power minus k b plus d times t. So then y of t equals, you will see that a lot of these terms nicely cancel out. A lot of these terms. So for example, e to the power k times b plus d times t cancels out with the negative exponent. K cancels out assuming k is not equal to 0. So I'm left with a minus c divided by b plus d plus m times e to the power minus k b plus d times t. And assuming, let's say at time t equals 0, y of 0 equals some value, y0, then I have y0 equals a minus c over b plus d plus m. So m, my constant value would be that whatever initial condition y of 0 minus this. So therefore, I have my final equation y of t equals to a minus c b plus d plus y of 0 minus a minus c b plus d times e to the power minus k times b plus d times t. That is my solution. And the beauty of this solution is when t goes to infinity, e to the power minus k b plus d times t goes to 0, and you're left with y of t going to a minus c b plus d, which is, sorry, this is not y of t actually. This should be the price function. See, these are some of the mistakes that you can make because you're so used to writing y of t. um, Also, let's not use y naught here. Let's use p naught. That's the original price. P naught, P naught. And let's make some changes over here as well. This should be P naught. So I have P naught and P naught, P of 0. And here also I have to make these changes. It's not y of t, it's p of t. It's p of t. So these are some silly mistakes that can happen, but very critical. So you see what's the beauty is at the equilibrium point, you get the actual value that we calculated before by just simply equating quantity demanded and quantity supplied, right, at equilibrium. But the beauty is at any given point of time, what is the price? Oh, that is given by this equation, and that you couldn't figure out by actually um, looking at just simply equating quantity demanded and quantity supplied. And that's the beauty of these first order these differential equations, specifically these first order linear differential equation. And that is what I have done here. Let's look at now, leaving aside all these n- algebraic terms, let's look at a numerical example of this market price pricing mechanism model. So we are told quantity demanded is a function of P, and that is given by 100 minus 2P. Quantity supplied is given by 20 plus 3P, and we are told the price adjustment coefficient K, it's called the price adjustment coefficient K, which is 0.5. So what is our model? dP by dt equals K times the difference between QD of P and QS of P. So K is 0.5, QD of P is 100 minus 2P, minus QS of P is 20 plus 3P. So what are we left with? 0.5. 100 minus 20 is 80, minus 2P minus 3P is 5P, dP by dt. So let's take the P to the left hand side so that I have dP by dt plus 2.5P equals to times 4 is 40, right? Now this is in the standard form. What is the standard form that we were talking about? This is the first step. In the standard form we had cos q of t. So in this case, in our case, it's in the standard form because p of t is a constant 2.5. Q of t is also a constant, which is 40, and our variable of interest y is actually price. Right. So what is the step number two? Step number two is figuring out what the integrating factor is. Integrating factor. So that is given by mu of t equals to e to the power p of t dt. So what is p of t? It's just simply 2.5 dt. So that is mu of t is given by e to the power 2.5 t. So what's step number three? Multiply this whole equation number one with the integrating factor such that it all boils down to the integrating factor times the variable of interest, which is p of t in my case, price, equals to, on the left hand side I have 40 times e to the power uh, 2.5 times t. So I integrate both sides to make um, price the subject, and then I can take 40 out. When I integrate my right hand side, it's t to the power 2.5t divided by 2.5 plus a constant value. I make T the subject by multiplying both sides by e to the power negative 2.5t. 40 divided by 2.5 times e to the power 2.5t plus c times e to the power 2.5t. So e to the power 2.5t cancels out, and p of t is 16 plus c e to the power 2.5t. Now assume at t equals 0, we are told its p of 0 is 10. Therefore, when I substitute in t of t equals 0, I get 16 plus c to the c. So c is therefore minus 6. Hence, my equation p of t is 16 minus 6 times e to the power minus 2.5t. And then you get into the interpretation. So you can just simply read through your note to check what different interpretations are. And then I have given other economic examples as well and few practice problems. And I would encourage you to follow through these practice problems, all covering first order linear differential equations. Different problems varying from price adjustment models that we did to population growth models and other models. Now, to make the note a little bit more comprehensive, I've also touched on nonlinear differential equations, especially using this method of separable equations to solve nonlinear first order differential equations. And I also talk about these exact equations as well, in addition to separable equations. But I'm not going to, and also equations that are reducible to linear when you have quadratic terms, like the Bernoulli equation specifically, and how we solve the separable equations, exact equations, like I have given examples in the note as well. But, however, I will not be covering and I will not be examining in the final exam this section on nonlinear differential equations. So you do not have to worry about this section. I will not be covering this section. However, it's good for you to just, if you have time, to go through it and to make the note comprehensive. I have given that. But at the end, I have given few more, so economic examples of nonlinear. Yeah, I have given few more worked examples. Maybe you can just, and practice some practice problems as well, um, for you to just, maybe if you're interested, to go through. But what I would suggest is in the Google Drive folder where I have given problems and solutions, lecture 10, maybe you can go through some of these problems, which covers first order linear differential equations, the standard form that we covered. So maybe you can go through some of these questions and answers and practice. Practicing is key. Now, this is the end of all your lectures. So in the final exam, I will have, like before, 7 questions, out of which you have to do 4, covering all these 10 lectures. So I have covered this by the end of July. It's July, end of July, so 26th July 2025. I think your exams might be in September, so you have more than a month to prepare. I've given a midsem, I've marked your papers and given your marks as well. Within 2 weeks, I had the midsem on 5th July, and by 14th July, uh, you got your marks. So you know where you stand. Practice, practice, practice. Next week, we can look at few more problems in general so that you get some practice, but you need to write and practice. So that's it from my end. Thank you very much. Um, and if you have any problems, or as always, reach out to me. Thank you.